Let's gather all ye faithful. Good afternoon. I'm Percy Diaconis, and very, very pleased to be able to introduce this talk by Maria Chudnovsky. Maria's a professor at mathematics department at Princeton. She works in combinatorics, more specifically graph theory, and more specifically structural graph theory. And within that world, she's the sun and the stars and the sky and the moon. She really, really is at the center of a big, healthy area of mathematics. I've had the chance to study some of her papers carefully and use some of her results, and my impression is, wow, somebody really spent all of that time and did all of that hard work and all of those ideas, and just makes me proud to be a mathematician, to be in the same world with her. And if anybody's earned the right to tell us about what makes a problem hard, it's Maria Chudnovsky. Please welcome her.
Hi, well, thank you, Percy, for this amazing introduction. I mean, you'll be disappointed. It's just there's no way to follow that. But thank you also for coming to my lecture, and of course, I thank everybody for inviting me. It's my pleasure to tell you what. So this is a public lecture, and it's all going to be sort of accessible and clear, but it will also be about the problems I actually work on now. So I'm hoping to be able to straddle both worlds and both tell you something that anybody who just likes math can understand, but also tell you what I actually do. And so thank you for giving me the chance to do it. I'm glad to have this opportunity. All right, so what makes a problem hard? Well, I'm a graph theorist, as Percy said, and the first thing I'm going to do is tell you that graph theory is an excellent branch of mathematics that has a lot of applications in the real world. The places where you would use graph theory in real life is when you need to solve an optimization problem, which is, of course, something we all do all the time. I listed here a few examples, but this is by no means a complete list of what optimization problems come up. So, for example, you need to plan a route. You're going from here to there, and you need to figure out what streets to take if you're driving, or what trains to take if you're taking trains, or what planes to take if you're in the United States and you're taking planes. That's something we do all the time, and that's something you could use graph theory to do. Another example, which is closer to, well, I guess planning plane routes is a very relevant thing at the moment, but another thing that's relevant to what we're doing right here, right now, is assigning rooms. Let's say you have a meeting or a university, and you need to decide which lecture will take place in which room, and you need to do it in such a way that you need to rent as few rooms as possible, but on the other hand, you don't happen to have two lectures being given in the same place at the same time. So that's another problem that you would use graph theory to solve. Matching workers to tasks, that's a very sort of well-known thing. That's an example we often give when we teach graph theory and optimization, that you have a bunch of tasks and a bunch of workers, and this person only knows how to do these three things, but that person only knows how to do those four things, and what's the right way to assign all those tasks, and maybe you also want to have your tasks completed with the cheapest cost, right? And different people charge different amounts for their work. So all of that is a problem that we often face, and it's a problem that you can use using graph theory. And the last one that I'll mention here is make a schedule. Again, going back to the world of conferences, right? Which talks to schedule in parallel? How do you make sure that out of 6 talks on one topic, not 3 are scheduled in parallel? So, okay, so these are all problems that we have all encountered. My personal favorite, which I'm going to tell you about, make a seating chart for a wedding. That's a personal story from my wedding. That's how I got favor in the eyes of my husband's family when I said, don't worry, I'm going to make the seating chart. And for those of you who do know graph theory, it's of course a coloring problem. And my husband's friends and family are all, well, our friends and family are all reasonably friendly, and they all more or less get along with each other. And so the graph of whom not to sit with whom is very sparse. And so then you can, of course, color it greedily and efficiently, which is something I could do, thus impressing everybody in the room. Okay, but if you don't know what I just said, that's okay. This was not a general public type of comment. Okay, so moving on. So I told you all of this you can do with graphs. What I didn't tell you is what a graph is. And this is kind of a difficult decision because, on one hand, it's a math meeting, but on the other hand, it's a general public talk. So I'm going to tell you what a graph is, and if you already know it, I'm sorry. And if you don't know it, then you're welcome. Okay, so graphs have vertices and edges. So you see some examples of graphs on these pictures. And then, right, so vertices are, we usually represent a graph as a drawing on the plane. That's kind of the most easily digestible way to see a graph. And some pairs of vertices are what we call adjacent. That means we draw a line between them. And some pairs of vertices are what we call non-adjacent, and then we don't draw a line between them. So I drew three graphs here. The first one is called G1. It has 4 vertices and 4 edges. Right, so at the bottom of the slide, let's see. So it's a challenge. Peter Winkler told me you can't use the pointer. Let's see if it's true. Yeah, no, I think Peter Winkler knows what he's talking about. Almost, okay. So here, this is G1. And these are the vertices of G1, A, B, C, and D. And these are what we call the edges of G1. So what are the edges of G1? They're pairs of vertices that you see in the drawing are joined by a line. So A is joined to B, so AB is an edge, and B is joined to C, and so BC is an edge, and so on. There are 4 edges. Okay, and by the way, they're not called whatever it says here. They're called vertices. This, unfortunately, is something I noticed right before the talk as I was going through my slides, so I apologize for that. Okay, so this is a graph, and this is a graph, and this is a graph, and you can draw them in different ways, and how you draw them doesn't matter. What does matter is what the vertices are, and then what pairs of vertices are adjacent, right? So in the drawing, they're joined by a line, but really, you don't need to draw anything. You can just record a graph in this form. Okay, so that's graphs. So now let's do an example in a little more detail. And so that's an example that we can all relate to. You have a conference, and you need to make a schedule, and you have constraints. The constraints are simpler than what we have here. So it's a 5-day conference, and you can only have 5 talks a day because, I don't know, that's how many talks I can hear a day. So that gives you 25 slots. And then you need, but you have more talks than just 25 talks, so you don't mind having talks in parallel, but you want to make sure that if 2 talks are related to each other, you don't schedule them for the same time. Okay, so these are the 2 constraints: 25 slots, and you don't schedule related talks for the same time. So what are we going to do? We're going to construct a graph where the vertices of the graphs are going to be the talks, and then the adjacency will be that these 2 talks are related. Talk 1 is adjacent to talk 2, right? I'm allowed to say that because the vertices are the talks. So talk 1 is adjacent to talk 2 if they're related. So now what's my goal? I want to partition all the talks that I expect to have at this conference into subsets, where each subset is what's going to be scheduled for the same slot. So what does it mean? In each subset, I don't want to have any edges, right? In each subset, I don't want any talks that are related to each other. So you want to partition the vertices of the graphs into sets. How many sets? 25. That's how many talks I have. That's how many slots I have. So that for every set, there are no edges. No edge has both ends in the same set. Now, there's something not real about this. I mean, many things. But one of them is I'm assuming I have infinitely many rooms, right? Like I'm assuming there's no upper bound on how many talks I can have in parallel. But that's okay. This is just an example. Okay, so, but that's a question we want to think about. So this has a name. That's a very well-known problem in graph theory. It's called a coloring problem, or more specifically, a 25 coloring problem. So why is that? Well, you imagine you color each slot with a color. So you color talks that belong to that slot with the same color. And so you have 25 colors, and you need to color the talks. And the rule is, as we already said, that talks in one color are not related. So talks in one color don't have edges between them. And another way to say it, and that's here at the bottom of the slide, another way to say it is each color is a stable set. So that's a word I'll use a lot, so I want to dwell on it for a minute. A set is stable, a set of vertices is stable. Sometimes people say independent if no two vertices in it are adjacent. So the 25 coloring problem is a problem of partitioning the vertex set of the graph into 25 stable sets. And the k coloring problem is the problem of partitioning the vertices of the graph into k stable sets, or determining that you can't, right? Some graphs, like if you have 100 vertices all pairwise adjacent, you cannot partition it to 25 stable sets. Okay, so that's the k coloring problem. That's a very sort of basic problem in graph theory. So here are some examples again. First, I have some graphs that are two-colored. So these are graphs where you can solve, right? The two-coloring problem has a solution. So here's this one. It has one color is blue and one color is fuchsia, I think. Or usually we color with numbers. There's color 1 and color 2. And this is a three-colored graph. So you can see 1 is a stable set, and 2 is a stable set, and 3 is a stable set. And now this guy at the bottom, that's a graph that's not three-colorable. Now, how do I know for sure that it's not three-colorable? So not three-colorable means the three-coloring problem doesn't have a solution. I cannot partition it into 3 stable sets. And how do I know that? Well, suppose the three-coloring problem, suppose I could color this with 3 colors. So I need to color the middle guy with some color. Let's say it's 1. So now I need to color the outside with colors 2 and 3. But they have to alternate, right? Because this is 2, this has to be 3 because they're adjacent. So this has to be 2 because they're adjacent. So this has to be 3 because they're adjacent. But it's a node cycle. You can't keep alternating 2, 3, 2, 3, 2, 3 on a node cycle. So that's not a three-colorable graph. That's a four-colorable graph if you can. Okay, so that was just some examples of what graph colorings are. So now, so graph coloring is one problem. It's kind of I think it's a problem with the nicest applications, but there's a related problem I want to think about, and that's the problem of finding the largest stable set, right? So in the k coloring problem, I want to partition into k stable sets. Here I'm asking what the biggest stable set in the graph is. Or I can be even sneakier than that, and I can say every vertex has a weight. And now I want the heaviest stable set. So what does it mean? It's a stable set, but every vertex, right, I don't just count it with weight 1, I count it with its weight, and I want the heaviest stable set. And this is, no, not there. And this is a fancy way to write it, right? So I want to find a stable set S with this expression maximized. I look at all the vertices in S, and I sum their weights, and I want to maximize that. So that's called the maximum weight stable set problem, and that's a problem I'll be coming back to again and again. So please keep it in mind, this problem. Okay, so coloring, k coloring, max weight stable set problem, they're all known to be NP-complete problems, right? So if P is not equal to NP, then there's no efficient algorithm, no polynomial time algorithm to solve them. On the other hand, it's not true that whichever graph I give you, it's hard to solve, let's say, the max weight stable set problem. There are some graphs where you can solve the max weight stable set problem. For example, here's a graph in front of you. It's a graph with no edges. Well, then I know what the max weight stable set is. It's the whole vertex set of the graph. So I solved it in constant time, right? Okay, so that's not somehow this problem. I know it's hard, but it's not hard yet. So here's another one. It's a graph which is a disjoint union of small graphs, right? So you should imagine there are many of those little components. So how would I solve the max weight stable set problem here? Well, in each component, I'll take the heaviest vertex. And I can do that because each component is only, at most, in this example, every component is only at most 4 vertices. So in each component, in constant time, I can find the heaviest vertex. And now I'll take the set of heaviest vertices in the components, and that's the best stable set, the heaviest stable set in the whole graph. So that's linear time. I had to look at each component, but each component I can do in constant time. OK, so again, easy. Let's keep going. Somewhere this hard problem should become hard. But so far, it keeps being easy. OK, here's another graph. That's called the 9-vertex path. So in case the drawing is not clear, it's 9 vertices. Consecutive ones are adjacent. Non-consecutive ones are non-adjacent. Right, and so you can imagine why it's called the path. You can imagine why it's called the P9, path of 9 vertices. So now there are many ways to solve the max weight stable set problem on this graph, but I want to show you a way that will generalize. So please bear with me. It may not be the kind of easiest way to do it. So I'm going to pick the middle vertex, right? It's a 9-vertex path. It has a vertex in the middle. And I'm going to what's called branch. So what does it mean? Branch, it means I'm going to do 2 cases. Case 1, when I'll examine all stable sets that contain this vertex. And case 2 is when I examine all stable sets that don't contain this vertex. Right, so that's this picture. So here, so check mark means in, X means out. So this is the case when V is in my stable set. So then the 2 neighbors of V cannot be in my stable set, right? Because you're not allowed to have adjacent vertices in the stable set. And now I just need to do this half of the graph and this half of the graph, right? And if I could solve this problem and that problem, and then I stick the vertex V in, and I found, what did I find? I found the heaviest stable set in the graph that contains V. OK, very good. So I'm going to put that information aside. Now I'm going to do it again here. So here I'm going to do the case, here I'm going to think about stable sets that don't contain V. So then I just delete V. And again, I look at this half, and I look at that half. And I find the heaviest stable set here and the heaviest stable set there, sum them up, write that down. And now I check, is the heaviest stable set that contains V heavier, or is the heaviest stable set that doesn't contain V heavier? And whichever one wins, I take. OK, so what did I do? I branched. And now I have 4 problems, but each of them is only half the size. And that's good. It turns out you can analyze this, and that gives you a polynomial time algorithm to solve this problem. OK, so still easy. Maybe not quite as easy as when there are no edges or when all components were small, but still definitely something you can do. So why is it? Why is this problem that's supposed to be so hard? Why does it keep being easy? OK, so here's a slightly more complicated graph, which is called a tree. So a tree is a graph with no cycles. Here's an example of a tree. Now, there's apparently a culture difference. I was told that mathematicians grow, so you see like this tree has a top vertex, which everybody agrees is a root. And computer scientists grow trees like that. They grow more like carrots. They grow into the ground. But mathematicians grow trees like that. They grow from the root up. So I'm going to take the computer science notation, and my tree is going to be a carrot. OK, so this is a tree. It has a root. Now, so trees are graphs with no cycles, just graphs that look roughly like this. And it turns out that the same idea works. You can always find a vertex that will break the graph into roughly equal parts. And you can solve the problem on this half and on that half, branching on this vertex, right? So you branch, do you contain this vertex, do you not contain this vertex? You solve the problem on this half and on that half, and that gives you an efficient algorithm to find the maximum weight stable set. OK, so very good. So that's somehow a little more interesting than, well, I can solve the problem on this graph because it has no edges. I can solve the problem on that graph because all components are small. So this is an actual interesting class of graphs where you can solve the problem. And now we can go further. Now we can say, well, what makes a graph like a tree? What causes the graph to have this nice property that I can delete a vertex, so maybe a small set of vertices, and break it into 2 roughly equal parts? Because that's what we use to solve the problem on the path, and that's what we use to solve the problem on the tree. So what makes a graph be like a tree? OK, so now this next slide, it's again, it's a little bit, has a split intention. So if you're not a mathematician, then you should just try to get the gist of this slide. If you know what a tree decomposition is, then you really don't need this slide. And if you knew and forgot, then this slide is really for you. So I'm going to try and kind of cover the whole spectrum of usages. So tree decomposition is a representation of a graph by a tree. So I consider all trees as being simple, as being easy graphs. And now I want to take a general graph and I want to see, can I find a tree, no matter how huge and how complicated, because all trees are simple to me. So can I find any tree to which this graph is close? Now, what does it mean when I say to which this graph is close? Well, that's the notion of tree decomposition. So what you're going to do, you're going to take your favorite graph and you're going to assign its vertices to vertices of the tree. So what you should imagine, you kind of hang a bag on each vertex of the tree, and you start putting vertices of your original graph into these bags, right? So it says here, T is a tree, and then to every vertex of the tree, I assign a subset of the vertices of my original graph, and there are rules, right? So there are some rules because I do want to represent my graph. I want to retain some information about my graph. So what do I want to retain? Well, first of all, I want to make sure that every vertex is assigned to a bag. Now notice it's different from putting things in bags because I'm allowed to put one vertex of my graph G into many different bags, but kind of. Okay, so every vertex of G needs to be in some bag. The second rule is every edge of G needs to be in some bag. For every edge of G, there needs to be a vertex of the tree that contains both ends of this edge. So far, this just tells you you have to put a lot of stuff in bags, right? But now there's a last rule, which kind of, it's a little bit of a counterbalance or counterweight, I guess. And what that says is there's some rules about not only put a lot of stuff in the bag, but also don't go too far, because if I have a vertex that's in this bag and in that bag, I have to maintain the property that it's also in every bag which is on the way between them, right? In a tree, I have two vertices in a tree. There's a unique path between them. So if I put the vertex V in the bag for A, and I put the vertex V in the bag for B, and then I look at the path from A to B in my tree, the vertex V has to appear in every bag along this path. Okay, so, all right, so that's what a tree decomposition is. Now, the gist of it is we're trying to assign vertices of my favorite graph to vertices of some tree, no matter what, preserving some rules about, so preserving some information about the graph. Now, okay, so here's a tree decomposition that you can always do. Take the one vertex tree and take your favorite graph and put all the vertices of your favorite graph in the bag on this one vertex. So that's definitely a tree decomposition. Every vertex is in a bag, every edge is in a bag. There's no path in the tree to worry about. But the thing is, you didn't do anything, right? Your bag is as complicated as the graph you started with. So that's not a representation, it's cheating. So, okay, so we won't note that. The goal is to say, I'm going to start with G, I'm going to put vertices in bags, and in such a way that the bags are much simpler than the graph G that I'm trying to represent. And we're going to discuss what much simpler means, but that's kind of the goal. So you represent by a tree, but so that you lost some complexity of your graph along the way. So what I want to do now is do a couple of examples, just because I'm going to be talking about this for the next, I don't know, 25 minutes, so it's good if we practice it a bit. So let's see. So here's one picture. The blue graph is G. The fuchsia graph is T, is a tree. And I'm going to try to represent G with T, right? So I'm going to get a tree decomposition of G using T. So by the way, I'm sorry I'm only pointing on this side, but I can only point on one side. Okay, so you can see that T and G are the same graph, right? I'm trying to represent my graph G with the same tree as G itself. So all I need to tell you is what goes into bags. And here's what I'm going to do. I'm going to fix a root. So here, I'm going to fix a root in G. So I'll call it 3. Now, every vertex of G has a unique path to the root. And then in this unique path, it has a unique neighbor. And what I'm going to do, I look at the vertex, I look at its unique path to the root, I look at its unique neighbor in that path, and I put in this bag the vertex and this unique neighbor. So let's see how this rule is implemented. So for example, vertex 1, its unique path to the root 3 is 1, 2, 3. So 1's unique neighbor in the path 1, 2, 3 is 2. So in the bag that corresponds to 1, I need to put 1 and 2. So here it is. In the bag that corresponds to 1, I need to put 1 and 2. Here's 4. Its unique path to the root is 4, 3. So its unique neighbor in this path is 3. So what I'm going to put in the bag that corresponds to 4 is 4 and 3. Here we go. And then 3, it's already there, so I'm just going to put itself there, itself in its bag. OK, so this is a 3D composition. You can check that it's really a 3D composition, or you can believe me that it's really a 3D composition. Now, it seems like we did not gain very much, right? I had a tree, and now I have the same tree, but now every vertex, instead of being a vertex, it now represents 2 vertices. So that's maybe not the greatest accomplishment. But what we did do is construct, for every tree, we constructed a 3D composition with all bags, where all bags have size at most 2. So that's, when you say it like that, it sounds better. OK. So now let's do this graph on the bottom. So that's a cycle. So the way I'm going to build a 3D composition for this cycle, I'm going to first delete the vertex 1, and I'm going to notice that it's a tree. And I'm going to use what we developed here to build a 3D composition for that. And you can see it's more like if you forget 1, then this is very similar to what we did there, not exactly the same. So now I need to add the vertex 1, right? I have some rules. I need to have all vertices. I need to have all edges. So now I have to add the vertex 1. Now I need to add the vertex 1. I also need to add the edge 1, 2, and to add the edge 1, 6. So I must add 1 to this bag, and I must add 1 to that bag, right, in order to capture the edge 1, 2, and to capture the edge 1, 6. And so now what? Well, now I recall the rule that if 1 is here and 1 is there, then 1 has to be everywhere along the way. So I'm going to add 1 to this bag and to that bag as well. OK, so what happened here? So something improved. I had a cycle, and now I represent this as a tree, which in my world is an improvement. You know, it was a 6-vertex cycle, and now bags have size 3, so that arguably is not such a great achievement. But notice we could have done the same thing to a cycle length 1 million. So here we really gained something with this representation. We took a graph which was more complicated than a tree, and we represented it with a tree. OK. So now I said we want to somehow make things simpler, right? We want to make sure that bags are simpler than the graph we started with. And the easiest way to make something simple is to make it small, right? We all understand that small things are less complicated than big things. So we measure, the classical way to measure the complexity of a 3D composition is by looking at the largest size of a bag. OK, so, and you say -1 because you want, well, I'll say in a minute why you say -1, but it's roughly the largest size of a bag. And then the tree width of the graph is the best width of a decomposition you can find, right? So you look at all possible tree decompositions for this graph, right? All trees, all maps, and you take one with minimum width. That's the tree width of your graph tree. Now, why did I want -1 in the width? Well, remember when we had the tree, we built a tree decomposition with bags of size 2. But we want to say trees have tree width 1. We don't want trees to have tree width 2. That seems wrong. So you fix it by putting a -1. OK, so and we will say that the graph has small tree widths. That means it's close to being a tree. That's kind of a tautological definition, but that's what we say. In particular, trees have tree width 1. OK, so very good. Now, why is that a good thing? Well, remember we said we could solve max weight stable set, for example, on a tree by removing a small set of vertices and breaking it into roughly equal parts. Turns out if you have a graph with small tree widths, with tree widths 100, you can solve max weight stable set, as well as some other problems, such as k-coloring, but some others. But let's focus on max weight stable set. You can solve max weight stable set on a graph with tree widths at most 100 by the same algorithm. You can find a set of 100 vertices, deleting which breaks the graph into roughly the same, into 2 parts of roughly equal size. Now you go through all possibilities of how your best stable set intersects a set of size 100, of which there are only 2 to the 100 possibilities. And now you solve the problem in this direction, you solve the problem in that direction, and you take the union. And that's called dynamic programming. So it's a theorem of Courcelle that for every bound on the tree widths, you can solve max weight stable set in polynomial time, right, on the class of graphs with, where tree width is bounded by that bound. So that's good for us. So small tree widths make the problem easy. Right? Remember, it all started with, we know max weight stable set is hard, but here and here and here are graphs where it's easy. So what is it that makes it easy? Well, for example, Crusell's theorem makes it easy. If you have small tree widths, you can solve the problem easily. Okay, so now I promised you that I would tell you what makes the problem hard, but I lied. I'm going to tell you what made the problem easy. I don't know what makes the problem hard, but at least I know what makes it easy. So we want to define different complexity measures on the graph, like tree widths, but also others. And somehow, if you think about it a little bit more from the point of view of structural graph theory, you want these complexity measures to help you represent the graph in some clearer, simpler way. But that's not something I can explain in 5 minutes, or probably not even in an hour. But what I can say in 2 minutes is that I'm looking for complexity measures that would have the property, if this complexity measure is low, then I can solve hard problems efficiently. That's something we all understand. And so let's stay with that definition of what a good complexity measure is. So tree width is one of them, and because of dynamic programming. There are several others. Tree width is not the only one. There's something called click width. There's something called twin width. There's actually a lot. Many of them are variants of tree width, but not the ones I wrote here. I specifically wanted to find ones that would be really different. So click width and twin width are really different from tree width. And so then what, as I already said, what I'm interested in is being able to say if some kind of width is small, then the problem is easy. And that, of course, is only interesting for problems that are in general hard. Right? If the problem is easy on all graphs, then that was a waste of my time. OK, so that's really what I wanted to talk about when I said I wanted to talk about what makes the problem hard. I wanted to say, well, actually, it depends on what object you're trying to solve the problem for, and it would be interesting to classify the objects into those where it's hard and those where it's not hard. So now I'm going to talk about that. So as we said, if the tree widths are small, we can repeatedly break the graph into roughly equal sized pieces, and that gives efficient polynomial time algorithms. I keep saying this because that's kind of the heart of everything. So I find when I listen to a talk, it's hard to kind of hear every sentence because you stop to think sometimes. But if there's an especially important sentence and it was repeated several times, then at least one time you wouldn't be still thinking about something else. So this sentence I want to repeat enough times so that everybody heard it at least once. Okay, so that's it. So now we're gonna ask the question: what causes a graph to have small tree widths? Right now that we convinced ourselves that somehow it's an interesting question, we're gonna the graphs that have small tree widths are an interesting class of graphs. Now we're gonna ask what causes a graph to have small tree widths, and that's going to be the second half of my talk. Okay, so in order to be able to answer the question, what causes something to have low tree widths, you need to know examples of things that have high tree widths, right? Because otherwise, maybe everything has low tree widths. What do I know? So this is a slide with graphs with large tree widths. Now, what's large? Well, large compared to their size, maybe, right? And, like if I have a 3-vertex graph, it's not going to have big tree widths, but not going to have tree widths 100. But if a 3-vertex graph has tree widths 3, that's kind of an accomplishment on the part of this 3-vertex graph. Okay, so here's the first example. It's the complete graph on n vertices. So you take n vertices and then you make them all pairwise adjacent. That's called Kn, the complete graph on n vertices. And however, in every 3D composition of this graph, you need to have a bag that contains all the vertices. So in other words, the only 3D composition for this graph is to take the one vertex tree and put all the vertices in that one bag. So that's a graph that's really terrible for 3D compositions, right? You don't gain anything. Okay, so noted. Kn is a bad graph for 3D compositions, has large tree widths. The next bad candidate is the complete bipedal graph. So what's a complete bipedal graph? You take 2 stable sets of size n, and you put all the edges between them. So okay, that's a graph. With this graph, what happens in every 3D composition? There's a bag that contains all of one side. maybe more, but you have to have a bag that contains all of one side. So again, you're not going to gain a lot. You started with 2 n vertices, and you need to have a bag with at least 10 vertices. That's not great. That's another example of what we call a graph of large triodes. Okay, so now let's pause for a minute, because so far, this is all very intuitive. If I'm trying to make something look like a tree, but the thing I started with has very many edges compared to its number of vertices, well, it's not going to look like a tree. It has very many edges. It's very dense, right? So everybody agrees that things that are very dense don't look anything like a tree. But now there's a surprise. There's a very sparse graph that still has very large triodes. And what this graph is what we call a wall. So I'm not going to tell you what a wall is, but I'm going to draw a wall for you. It's made of bricks. And this is a planar cubic graph, right? So it's so sparse you can draw it in the plane without intersections, and its max degree is only 3. And yet its triodes is square root of its size, which is still big, right? So if you take this wall, right, so you understand what it means to be an n by n wall. It has n bricks like this and n bricks like that. And that wall has triodes n. So, okay, so that's something that at first is counterintuitive, right? It's a very sparse graph, and yet it has large triodes, but we have to record it in our inventory of graphs of large triodes, right? If we're going to try and understand what causes large triodes. Now, you can make it even more surprising. You can subdivide every edge, right? You understand what subdivide means. You put vertices along each edge. So now I made it even sparser, right? And I used to have a graph with all degrees 3. Now I have a graph with some degrees 3 and some degrees 2, right? So the density is very, very low. And still its triodes is huge. Subdivisions don't help, don't change triodes very much. Okay, so that's another example of a graph with large triodes. So now let me show you the last one. The last one is a little bit different. So the last one, if you know graph theory, then the last one is the line graph of the second last one. If you don't know graph theory, then you get the last one from the second last one by changing every vertex of degree 3 into a triangle. It used to be when I was a graduate student, there was this delta y operations and y delta operations, and it was a very kind of, I don't know, it felt to me like you need to come from a tradition to know about delta y and y delta operations. It's not just for everybody. And so here I am, 20 years later, talking to you about delta y operations. I feel like I've accomplished something. Okay, so to get the bottom graph from the third graph, you do y delta operations. Every junction that used to look like a y, you now make it look like a delta. You make it look like a triangle. Okay, so that's another example of a sparse graph with large triodes. So now let's see what we can say about them. Okay, so remember what I want to say is triodes is big if you contain one of these examples. Well, there's somehow, there's an obvious answer to this question. Triodes is big if I contain something of big triodes. That's obviously not the answer I'm looking for, but that's an answer. So what's the difference between the answer I want and the answer you have large triodes if you contain something with large triodes? Well, what you want is to come up with minimal things of large triodes. You want to kind of trim down your list so that you need to contain something from this list, and there's no redundancy. You don't have 2 things in the list so that one contains the other. So let's think about that now. Let's think whether this list is minimal in the sense that nothing in the list contains something else in the list. Well, if I'm going to say that, then I'm going to need to know what contains means, right? Because probably most of you know that there are many different containment relations in the world, and so you need to ask what I mean by contain. And so let's start with kind of the most well-known one and the most intuitive one, and that's the relation of being a subgraph. So you start with a graph, and now I want to say what it means for another graph to be its subgraph. And all that means is you're allowed to delete vertices and you're allowed to delete edges. Right, so that seems fair. Right? H is a subgraph of G if the vertex set of H is a subset of the vertex set of G, and same for the edges. So there's an example. I have this graph. It's a subgraph of that graph, because what you do is you delete the middle vertex and all the edges attach it. This is also a subgraph of that. because what you do is, right, so this is like it's 2 5-gons, one drawn like this and one drawn like a star, so delete the edges of the star. Okay, so that's one containment relation. And it turns out that for this containment relationship, there's sort of everything is clear with trivids. It's clear what's minimal and what's not minimal. It's a theorem of Robertson and Seymour from the 90s, that if your trivid is large, it's because you contain as a subgraph a subdivided wall. So I redrew here a subdivided wall. So for every C, there's some T, right? That if your trivid is bigger than C, then you have a wall of size T, a T by T wall. And about maybe 10 years ago, there was some work on trying to improve the relationship between the C and T. And the best bound currently is due to Chikouri and Chudnovsky. That was actually a very big deal 10 years ago, because Robertson and Seymour had exponential bound, and Chikouri and Chudnovsky had polynomial bound. And it's it's a big difference in many ways. Okay, so for subgraphs, you just need to think about the subdivided wall. Now let me go back here. So what happens? Well, if I exclude, so let's just understand, I had all these examples of big trivids. How come it's enough to think about the subdivided wall? Well, the thing is, if I contain this, then I also contain a subdivided wall, right, as a subgraph. I'm allowed to delete edges. So I don't need to list this and that separately. Arguing that I would have, like if I want to say, if you don't have this, your trivid is small. Well, if you don't have this, you certainly don't have that, because this just has more edges than that does. And it's a little harder with this guy, but it also works. And finally, for this one, same deal. The subdivided wall is a subgraph of that, right? Because to go from deltas to y's, you just delete one edge from every delta. Okay, so there's only one serious, serious example, one serious family of, or one minimal family, I can say the real word. There's only one minimal family of graphs of large trivids if your containment relation is subgraphs. So now let's go on. We already did all of this. So now I want to move on to a different containment relation, and that's the containment relation of induced subgraphs. Now, I think, as far as I understand, induced subgraphs became popular maybe in the last 25 years. They kind of were considered this very local thing where you just look at small sets of vertices and say something about them, and then slowly people understood that actually it is not the case. They do have global implications on the structure of a graph and so on and so forth. And so in the last 25 years, the field of induced subgraphs is flourishing. And so having said that, let me tell you what it means to contain something as an induced subgraph. So for subgraphs, you are allowed to delete vertices and delete edges. What you're allowed to do now is delete vertices. But once you start with a big graph, and you say, I'm only going to look at this subset of the vertices of my big graph. But now that's the only decision you can make. If two vertices that you decided to keep were joined by an edge, you have to keep this edge. You can't just say, and also I'm going to delete this edge. So let's say this more precisely, more rigorously. So H is an induced subgraph of G if the vertex set of H is a subset of the vertex set of G. And then two vertices that I decided to keep in H are an edge of H, if and only if they were an edge of G. Obviously, you don't add edges, right? That's kind of, nobody thinks you should add edges when you do containments, but you're not allowed to delete edges either. Okay, so now in that picture, so we already said of this, only that one was minimal for subgraphs, but under the containment relation of induced subgraphs, they're all minimal. Each of these families is minimal under induced subgraph. Nothing contains anything. Okay, so that means it's somehow much harder. Right? At least we already have 4 minimal families of abstractions. Okay. So that's what it says here at the bottom. But actually it turns out that for induced subgraphs, there are many more families of abstractions. And I'm going to show you some. So there's this guy. So it's you take n or n paths, and then you take n vertices, and you give each vertex one neighbor in each path. And if you know graph theory, you can see this has large triodes because it contains K and N as a minor. And if you don't know graph theory, then you can believe me that it has large triodes. And yet it's not contained in anything that we saw before. And it doesn't contain it, and more importantly, it doesn't contain anything that we saw before. Here is, so okay, let me just say one other thing about it. So you can make this a little bit more interesting. Here I gave each red vertex just one neighbor on each path. You can actually give it as many neighbors as you like, as long as they're separated, as long as like each vertex has an interval where all its neighbors live. And the reason to do that is if you don't make these rules, then suddenly you might contain something else, right? So that's just to attain minimality. Okay. So now here's another example. This is called the Death Star. Right, yeah, it's a little graph theory humor. I'm not going to explain it, but this again, the triodes of this is as big as the number of vertices drawn vertically. And then there's another example we know at the moment, which is called layered wheels. And I'm not going to explain what that is because that's way too hard. But ironically, the layered wheels, which are by far the hardest example we know, were the first non-classical example that was found. Okay. So what are we going to do? There's this family and this family and this family. Well, we somehow need to unify them, right? We need to prove some theorem that says, here are 7 types of things that if I don't contain them, the triodes is bounded. That's what I'm looking for. Okay, so how would you go about that? Well, Lozhin and Razgon made the first stab at it. And they said, well, what if I'm only allowed to exclude a finite family of graphs? So in particular, that means I can't say words like subdivisions. I can't say I'm going to exclude all subdivisions of a wall because that's an infinite family, all subdivisions. So it has to be something else. So then that means they need to find a finite family of graphs so that each of these guys contains a representative from it. And also each of these guys contains a representative from it. And that's a lot of rules. That's a lot of things you want from your one poor finite family of graphs. So they could prove an if and only if theorem. If you exclude a finite family and you want to get bounded triodes, then your finite family must contain a complete graph, a complete bipartite graph, a graph, sorry, wrong button, a graph that looks like this, and a graph that looks like that, which means it's obtained from this by a y delta operation. Okay, so that was a very nice theorem, and it had an especially nice proof because it had a proof that you can generalize very, very far. So I'm not going to, this is not the time to tell you about it, but I'm just going to tell you that this proof contained some lovely, lovely ideas that you can take and run with a lot. Okay, so let's recap where we are. So we're trying to ask what you need to exclude as an induced subgraph to get bounded triodes. We had some examples such as the big clique, a big complete bipartite graph, subdivided wall, and the line graph of a subdivided wall. And we know we need to exclude one of each. So now suppose I've excluded one of each, right? So I excluded KT and KTT and the subdivision of WT and the line graph of a subdivision of WT. And now the question is what else, right? That's where we are. Now we are at the what else stage. So from now on, I'm going to assume that I've excluded this, we call them basic abstractions. So I'm only going to think about what we call T-clean graphs, which means graphs where the things we know we already excluded. Now what are we going to do? Right, okay, so let's think about that. All right, so the first thing we asked, and so now we are up to recent theorem. Lozhin Razgon is maybe about 5 years old, and now it's going to be more recent than that. So the historical retrospective is over. So the first question we asked is, well, what if I look at the T-clean graph, and now I'm allowed to exclude one more graph? What should that graph be? And it turns out you can analyze it exactly, and that only works, right? That only guarantees bounded triodes is your one more graph looks like this. It's a graph where every component is a subdivided star. Not necessarily a star with 3 rays, but some star. Okay, and that's, oh, right, I didn't say anybody's name, so I'm not going to say any names now. But, so Then we said, well, okay, we did one graph. What about a finite family of graphs? So I'm looking at the T-clean graph. I excluded the basic abstractions. Now I'm allowed to exclude finitely many more graphs. What should those graphs be? And again, we can get an if and only if theorem, which I'm not going to burden you with. But there's a nice corollary that I am going to burden you with. Excluding the following nice-looking family works. So what is this family? So you take a bunch of paths, and you take a vertex, and you give it a neighbor in each path. So here it is. And so far, that's one graph that I built, right? It's a bunch of paths and one vertex, and it has a neighbor in each path. That's one graph. Now I'm going to turn it into a finite family. How am I going to turn it into a finite family? I'm going to say to the left of this one neighbor that I picked, this vertex is allowed to have whatever neighbors it likes, right? So where there's this pink-colored squiggly edge, that means you're allowed to have any neighbors that you like. So that's finitely many decisions, right? Have this finitely many paths, each of them has finite lengths. So now, if you understand this drawing like that, it describes a finite family of graphs. And the theorem is, a corollary of the theorem is every finite family like that works. And you can, like I said, make it if and only. Okay, so that's one thing. So now let's go in a slightly different direction. Well, I know I have to exclude the T-basic abstractions, a big wall and the big line graph over wall. What if, and then like there's some other abstractions I need to deal with. Well, what if I make my life easier? I exclude a fragment of a basic abstraction. I don't say you don't contain a T by T wall. I say you don't contain something that every T by T wall contains. Right? So that's an easier problem. I've excluded a smaller thing, so I'm looking at a smaller, what's left is a smaller family of graphs, so that's an easier problem. And you can have more fun with it. So if I now, let me not explain it, but let me just tell you that this is a fragment of a subdivided wall. Every subdivided wall contains one of those. And this is a fragment of a line graph of a subdivided wall. Every line graph of a subdivided wall contains one of these. So let's say I exclude this and I exclude that. And I exclude KT. So then what can you say, right? What else? What else? And then again, there's a nice answer to that. What else is a forest? If you exclude this little fragment and this little fragment and a big complete graph, and you exclude any forest, then your tree width is bounded. So that's kind of a different way to get at, right? How do we tame this huge world of abstractions? And the last thing I want to say is that you can maybe make your life a little bit easier by just changing the question a bit. Right? Because our motivation for looking at tree widths was to find something that allows you to solve hard algorithmic problems efficiently. Well, it turns out that if instead of asking for bounded tree widths, right, for tree widths at most 100, you ask for tree widths which is log the number of vertices, algorithmically you get the same effect. And to that, we have many fewer possible abstractions. Most of the examples I showed you actually do have tree widths which is at most log the number of vertices. So you can try and attack that problem. And then the problem with attacking that problem is that the classical methods from the 1990s don't work here at all because they were, to them all numbers were the same, and to us suddenly we have a logarithm, and that's okay. But 2 to the logarithm is suddenly not okay. 100 and 2 to 100, they're both small. Log n and 2 to the log n are of very different nature. But on the plus side, right, so like the methods don't work, but the problem is definitely more tractable. So. And then there's something else that I'm not going to tell you about, but it's a variant of tree widths, which is called the tree independence number. And what you do there, instead of, so it's something that was specifically designed to solve the max weight independence set problem, the max weight stable set problem. Instead of bounding the size of every bag, you bound how big a stable set it contains. And turns out that's another interesting question you can think about, which I'm not gonna go into, but it's a nice question. And again, helps with algorithms. And thank you very much.
Thank you, Maria.
Thank you.
We have time for questions. And if you want to ask a question, there's a microphone over there and a microphone over there.
Yeah, are there any connections between the tree width and more traditional invariants like the homology groups of the graph?
I'm sorry, say it again?
Any connections between tree width and homology, first homology rank, for example?
I don't know to answer this question right here, right now. I suspect there are connections, but I cannot answer this question.
Before this lecture, if you'd asked me how far a graph was from being a tree, I would say the rank of the first homology group.
That is exactly why I'm convinced that there are connections. But,
At the beginning, you told us some problems that are hard for all kinds of trees, and then you spent most of the talk talking about classes where they're easy. But how do we know those original problems are hard?
oh, for that you should ask the classics. For that you should ask Richard Karp.
There are proofs.
They're proofs, yeah, they're proofs. Yeah, I guess I should not be joking around. It's been proved.
Just to stick in a question from the introducer, I remember that computing the tree width is a hard problem. Is that right? Just the question of, here's a graph, what's the tree width of it? That's a hard problem.
That is a hard problem, but luckily for us, what's an easy problem, if you give me a graph and you tell me it has tree width 100, it's easy to find a tree decomposition of width 100. And so in order to solve these algorithmic problems, it's enough to know that the graph has small tree widths. You don't also need to, every time go back and look for an algorithm to find a tree decomposition.
I was going to ask the same thing. I mean, how much easier does the problem get if you sort of need it handed down from high, that you're already working with a graph that has this tree width decomposition? Is it like you're just applying this to families of graphs where you can reason in some other way about the tree width decomposition? Or like how useful does this become when you need sort of this additional obstruction and then you have to make reasoning about that obstruction, which is in itself like sort of difficult to talk about? By which I mean like tree width is difficult to compute, then.
Right, but the thing is, if tree width is bounded, then it's easy to find a tree decomposition. And so once you're handed from above that the graph you're working with has small tree widths, you're in a completely different world. Did that answer your question?
Yeah, I think that.
Okay.
I think this is the last talk of our meeting, and we would thank you for inspiring talk, and I'm inspired, and I'm going to go read more. Thank you very much.
Thank you, Percy, and thank you, everybody.